The Mars Ascent Vehicle, or MAV, is a sample transportation vehicle that will launch from the Martian surface and transport ground samples into a low Martian orbit. NASA was concerned that their choice of propellant for the MAV would freeze on the surface of Mars. AAE251 Team R303, consisting of Haley Scott, Hannah Pike, Jeanette Snyder, Joseph Schubach, Kristen Stava, and Maxwell Lowe, have developed a new design for the MAV. This presentation details the process we used to make this design.
The stakeholders of our design are as follows. NASA is the main stakeholder. They are our client and will be using our design. The NASA employees will be the controllers of our design. The United States government and taxpayers are the financial funding for the project. They are seeking a financial payout from the mission in exchange. SpaceX is both an ally and a competitor of NASA, so they will use the experiences from our mission and the information we learn in their future missions. The California Institute of Technology, Northrop Grumman, and the European Space Agency invested money in the mission and requires recognition for their contribution. The European Space Agency and various research organizations will use the sample transported by the MAV to make scientific discoveries. Space enthusiasts will also be interested in hearing the results of the mission and the scientific advances it can make to the world. The design must fulfill certain requirements. For one, in order for the MAV to be transported to Mars initially, it must not exceed the size or weight of the previous MAV by more than 10%. It must be completed by the end of this year to be made in time for launch, and it must be durable enough to fulfill its mission without damaging the samples it will carry. It must launch the 14 to 16 kilogram payload into low Mars orbit, have multiple stage design, operate with minimal instructions, and be easy to use and emulate. Most importantly, it must return the samples safely, communicate the results, and give credit to other organizations.
When in travel, a Mars Ascent Vehicle could encounter atmospheric debris, micrometeoroids, Martian dust, and poor space conditions, which could damage the spacecraft structure. We would create a more durable and sturdy structure that could withstand these outside dangers. It could also experience atmospheric drag that would pull it out of orbit. To avoid this, we would keep the spacecraft in a higher orbit where the drag is minimal. Another risk is radio interference, which cause a loss of communication. Our solution to this is to make it able to operate more independently and without communication. Galactic cosmic rays could cause damage to electronic equipment, but we would install reflectors to absorb the particles. And extremely low temperatures could cause the propellant grain to freeze, but to avoid this, we would install a heating system. All of these mitigations would increase its chance of having a successful mission.
After determining the mission's criteria and risk along with the spacecraft's requirements, the team brainstormed several potential solutions for the MAV's propulsion system. We proposed a reliable liquid fuel rocket burning liquid oxygen and methane, an experimental hybrid design of liquid oxygen and polyethylene, and a stable two-stage solid design of ammonium perchlorate and hydroxyl-terminated polybutadiene. For all of these designs, we began by sketching a potential shape for the rocket as shown by the side, top, and cutaway view above.
Determining a high likelihood of selecting a two-stage design, combined with tables detailing the performance for various rocket types based on past research, we were able to approximate the required delta V for the MAV as 3,350 meters per second. Concurrently, we wrote a code capable of determining the total initial mass of the rocket, as well as the ideal distribution of masses for a two-stage design. Our preliminary results suggested that the rocket would be around 70 kilograms, with the delta V split 50-50 between the first and second stage. Armed with our prior research and code, we were ready to make an informed selection of our rocket's propellant.
While all three proposed designs have reasonable projected values for initial mass and sizing, not all of the designs measured up well against our determined mission requirements. Specifically, the liquid and hybrid designs did not meet the long-term storage requirement. This is due to the feasibility of storing a cryogenic substance for a long period of time on the inhospitable Martian surface. Additionally, the hybrid design did not meet the durability requirements due to the complexity of a hybrid rocket and the stresses involved in launching from Earth, transit, and landing on Mars. Given our requirements, we settled on a proprietary solid fuel from Aerojet Rocketdyne known for its performance after a long period of exposure to cold temperatures. Using this particular solid propellant in a two-stage design results in an ISP of 277 seconds and an initial mass of 61.75 kilograms, which was well within the mission constraints of reaching an orbit of 12.35 kilometers and having an initial mass under 400 kilograms.
The final design of the Mars Ascent Vehicle as it will be delivered to NASA will be a two-stage solid propellant rocket. The dimensions of the rocket will be 2.07 meters in length by 0.30 meters in diameter. This is below the maximum size constraint of 2.8 meters by 0.57 meters by 0.57 meters. The total mass of the rocket will be 60 kilograms, which is below the constraint of 400 kilograms set by NASA. The predicted specific impulse of the rocket will be around 277 seconds. The frame of the rocket will be constructed of carbon composite and aluminum. The total delta V delivered by the launch vehicle is 3,169 meters per second. The propellant used will be a new experimental propellant developed by Aerojet Rocketdyne, advertised as being resistant to damage from cold soak. The 3D models of our rocket show a basic rocket ship with two stages, the second stage being approximately half the size of the first stage. As seen in the cutaway, both stages will use essentially the same design, utilizing the same type of nozzle.
As a team, we learned many lessons over the semester. We learned very quickly that we needed a strong, centralized form of communication. Our group chose to communicate over GroupMe and Zoom calls. These tools allowed us to accomplish team goals during the challenges of the coronavirus pandemic. To begin our design, we learned how to write an accurate and detailed list of needs and requirements to evaluate the performance of our design. We also learned how to calculate various parameters like orbits, launches, stages, and other astronautical needs. The team also learned about propulsion systems and how to choose a propellant type that best fit the needs of the mission. We utilized the 7-step process for rocket design in the creation of our MAV prototype.